かこっちはね。はい、じゃあとりあえず始めましょうか。Good morning, everyone. Good morning. Good morning. Let's start today's seminar. Today's seminar presentation is belongs to Mr. Maya, Mr. Tomori, and Mr. Oscar. Let's start.
The first example looks at what might be the impact on an income tax reform. This table shows the income structure of the sample differs from the income structure of the total taxable population. This structure example, this rate is 21%. This rateなので、weighted sample is and 26. In the same way, these are calculated.
This operation is to change to fit elemental data. Yes, national tax to sample. Explain this.
あ、これが、ドイツの、国民党で、こっちが、インタビューして取ったデータで、 キストにあったのはだいぶ
Maybe the sum of all presentation will be 100%. So maybe this is you only present this number in the integer number, not the real number, so that the sum of all presentation is not equal to 100%. Maybe if we divide it 30 divided by 140, it is not exactly 21%. Maybe we must have a significant number so that the sum of all this presentation will be 100%. If we sum 21 plus 35 plus 29 plus 40 will be equal to 90%, only 90%, because we omitted the significant number of decimal number. So maybe the representation of the present of the number will be real number, not the integer number. Like in the second, the sum is 101%, not equal to 100%. Also in this 101%. Maybe we make the round it to the greatest integer, so we not have the 100% in the sum of all presentation. Maybe it is better to represent the presentation in the real number. So we must count the decimal number also, so that the total of the presentation is 100. Because this is the percentage of this related to the weight. The sum of the all weight must be 100%. Maybe this only in this example, Mr. Maya only use the integer number, but maybe is the correct value is the real number. Maybe it is only the use of the number. Maybe the later we must represent the percentage in the real number, not in the integer number.
Maybe 35%, 50 per 140
Yes.
is near to 36%. It is exactly 35.7143.
Yes. So we must include the decimal number.
Rounding error.
Yes. Okay.
So, even after debating, there remains some differences. To calculate tax bill taxable income is calculated. Taxable income is gross income minus allowances and deductions. These allowances and deductions include, for instance, part of the social security combination, but also allowance for children, old age, the cost of education, expenditure on commuting between home and job, and many more. This blue line is the marginal tax rate in the 1995 tax laws, and this red line is in the 1995 tax reform. Tax due is calculated by using tax rate which depends on taxable income, and the persons are divided into 13 classes with item of tax due. Then the total income revenue is estimated with a smaller error. On applying the 1995 tax reforms, the total income tax revenue was reduced by 20 billion. If we have doubled the allowance for children in the 1990 tax law, the total income tax revenue was reduced by 14.4 billion. If we have abolished the split rule for married couples in the 1990 tax law, the overall gain is 67 billion.
ドイツマルク。
currency German. Oh, that's wrong.
It is quite difficult to prepare a microdata file for use even with static microsimulation. Once microdata files are prepared, static microsimulation can be done by means of quite straightforward algorithms. Next example. We consider the question, how many people 60 years or older will have adult near relatives who could nurse them if they needed care in the middle of the 21st century. We use individual data and apply birth, death, and marriage probabilities when we simulate a complete kinship network to answer this question. The database is updated at this page. Birth enters a new individual record into the database and update the father's and mother's record with information about the newborn child. This marks a person as dead and remove him or her from the database. Marriage and divorce update both partners' information. After a number of simulation steps, we can trace kinship relations back. Conclusion. Some 40 years from now, the percentage of persons above 60 years of age without a partner and without children will be about 2 times the current percentage except for the oldest. Thank you for this.
Oh. 聞かれました。全員で。
But the meaning of this example to what the purpose is example. Traditionally behind the point. So the last example and this.
スターティックマイクロシミュレーションは、国民登記からデータを抜き出して、データを使ってシミュレーション。1月のような
じゃあ問題となるので
はあるんですけど、状態遷移確率が与えられて、これによってすぐデータが計算される。
データベース前のやつはそのデータベースの更新みたいなのが 今回のはそのデータベースがフィックスされている、常にフィックスされていくっていうことです。
データベースの更新とデータベースのフィックスって違うんですか？
フィックスと
同じのかな？
僕が言った意味では同じ文脈、同じことです。更新というか調整というかっていう更新
Update? Is there any difference between update and fix of database? Is his question. His question.
Okay. This impression. Okay. Shall please next present.
Wait a minute.
Mr. Omori, did you upload your file to
ああ、
calendar?
先週あれがあげた先週の
あります。
And please upload it by PDF file. And please add the page number to your slide.
ああ、そう。
すみません、ありますね。
ああ、いや、あれをつけて、ページナンバー。Wait a minute. I'll upload some. I will upload PDF file. I uploaded. So please show and then you can.
Where we can find.
Oh? Okay? Oh, sorry. Okay. Okay. Now let's start my presentation. My chapter is the queuing models. This is contents. First, I talk about the outline of queuing models, and then I provide some airport example, and then finally I explain queuing model. This is one of example of some queuing, such as queuing is in Japanese 行列列 then 行列 and then this image is such as one of fast food shop. Please imagine in this server is the one of counter, and this queue is this queue is a line of some customers, and then if the process of in this image. Now first, this customer served by this server. This black point is served customer, and this white circle is no served customer. And then served customer. Next action is go now. So such. And then next, move ahead to the food. Such. The next, new customer join the queue. Such. The next is server customer, such as. So such repeat this this route. This is the image of some queue. But anyway, this image is the same flow of the process of queuing model. The process of queuing model. In this is this shape is please preference. this customer, the mean is it serves some service on the server, such as account or to process, such as printer jobs and computer jobs, such as waiting queue. And the server is server customer, such as some bank officer and some shops, and such as some processor and some core to serve those customers. And this is queue. The queue is the line of waiting customer to be served. And this agenda is the list of the event schedule to occurs. And this agenda is pushing service. This flow is same as back pages flow, such as queue. And then in same time agenda such generate new events and insert into the agenda, such as. But remove past events. So one first stage occurred event is removed, such as. And next then. Customer F joins the queue. This event is occur and remove. And some new event is generated and join to insert the agenda. So this process is queuing models, such as. And this is a diagram of queuing model. This figure is this figure is come from the text. I already explained this queue is the line of some customers, and the customer is to be served, and this server is to serve some customers. And this source is generate new customer, and the sync the point of customer disappear from the system. In this three object, and queue, server, and customer in this model happens. The queue and server as a static object because not this object will not move. But the customer is a dynamic object because the customer is moving source to sync. So in this model process is expressed by customers moving. So customer comes source to sync, and then wait to be served. If customer served, go to sync. This is the diagram of queuing. Now then, I explain some steps of the other models before account of the steps of queuing model. Differentially equal model if the steps of the time is such cumulative time. If time by the time to change some values. The other system dynamics and micro simulation model is such discrete and equidistance time steps. So such day 1, day 2, day 3, day 4, 1 hour, 2 hour, 3 hour, 4 hour, such as. And then time steps of Turing model is time goes by event to event, event 1 to event 2, event 2. So in this it's not equally time. Event to event. This is the steps of Turing model. And then I explain some process of Turing model. The process, the Turing model is distinguished 3 sub-process. The first is arrival process. This process is explain about when customer comes and how many customer comes and what moving of customers. The second process is waiting process. This is FIFO or LILO. This is
This is called FIFO.
The
あんまりそっちは言わない。
And the last sub-process is this is the service process. This is the mean is the number of server, such as the number of counter, or number of processor, or number of jobs member, or so on. And the time to serve. Each counter not equally if by the case. So in this case, not equally the time to serve. The first arrival process. Arrival process is characterized by such elements. The number of arrival customer is finite or not. If finite, one day and finite open shop, such bank, post office customer, not bank ATM, because some ATM is 24 open. So please imagine some finite opening shops. And the next is types of customer is only one or several. Easy. Printer jobs are printing, scanning, or copying. Such customer is not equal. So if this case, not one, and this is a similar one, similar. And the next, the customer demand is only one or several types. Easy. In airport, customers are having baggage or not. If having baggage, customer is such some example. The next arrival distance is deterministic or stochastic. the stochastic mean is the distance follows some distribution, and deterministic is equally time steps. In these elements, it's characterized arrival process. But then I explain some waiting process. Waiting process is characterized by then FIFO and or error. I'll show some animation. So please understanding by this animation. FILO is the meaning is fast in, fast out. So the first member of the queue is gone away, and the last point new customer coming with such as, and this is LILO is the last in, last out. Such. In last point, the last of queue customer is go away, and the same point some newly customer coming, such as.
Show me again.
Yeah.
This is actually FIFO. Please then. Oh, this is not LILO. This is LIFO.
LIFO.
LIFO. Last in, first out.
So
This is stack.
this stack is not LIFO. LILO.
ライロってないよ。ライフはあるよ。うん。
If it's first in, first out, and last in, last out, after these two are equivalent. So it should be last in,
Last
first
in,
out.
first out.
Last in, first.
トイレ先出してね。
そうそうそう。
ラストインラスト
うん、それライロってないよ。ライロだファイフと同じだよ。
ラストインラストファーストインファースト
うん、同じ同じ。だから、本部にもライロなんかないよなと思って。ファイライフォ、LIFO。
Last in, last in, first out. So last.
最後に入ったのが最初に出るってことね。
最後に入ったのが
最初に出る。
最後に入ったのが
最後。最後に入ったのが最後に出るのは同じことでしょ。同じこと。そうよね。最後に入ったのが最初に出る。
じゃあね、これは FIA ピューだから
なんだろう。ファースト、ラストの
は合ってるけど、名前が
意味をちょっと間違えた。
ラストインラストアウトって書いてあるの。いや、資料の
これは間違いない。
2個目のラストが、それがファーストだよっていうだけで、図っていうか。
図は合ってる。図は合ってる。
もう一回見せてもらっていいですか。
This is start. Last in, first out.
Last in, first out. This is it?
Yes.
So
アニメーションは合ってる。
this here is correct, but this account is
So,
not.
But I didn't had this word.
Sorry. So this is not. So please please remember this animation. As such, the file or LIFO is characterized. And
the rule of FIFO, first in, first out, or first come, first serve, we can observe in the reality. Maybe in bank, the first customer come, he or she is first to be served. But in the case of LIFO, what is the example of So the first customer will be served immediately. So what kind of the system of queue can follow this rule?
this
LIFO. Maybe in the usually real phenomena we can see the FIFO, first in, first out.
yes. So this is usually.
Usually, yes.
But I
Can you give-
seek this example, but I don't. So please some comment about it. Please.
What is the
Could you-
Maybe it's a stack and you have a stock of bottoms. You want to sell those bottoms. And you can only push the bottom from one direction. So customer will always take the
first,
toughest bottom
the top.
out. So it's last in, last out if you buy something. There is only one exit, one way you can put something and get out something. It's a stack.
確かにでも後ろから起きますよね。
One type is automatic.
Push down
Push down automatic.
They also use it to solve some problems about mathematics, such as they want to start a step and instead sorry. It has some sequence such as third, second. If we decide we put them as A, B, C, D, and we set that it when we set beyond to them, we can pop it and we send another one into the stack. The stack also used to solve such problems.
This is a kind of layered task.
Top and into.
Okay, thank you very much.
So the system of by the Mr. Deguchi, I explained some vendor system to explain about automata. I think so. The vendor system is some last in, first out. Mr. Deguchi said. This is characterized about the waiting process. And the next characterized point element is waiting queue is finite or not. This is queue is finite. And then the last is service process. The service process is characterized by such element. The available server is only one or several. Some only one or several. And types of server is only one or several. As airport, imagine it has general service steps such to information counter, check-in counter, security counter, and check-in counter, and such as. So many processes they have. And the next is serving rate depend on customer demands or customer. By the additional service, the rate will change or not. This is the need. And the next is the serving time is constant or stochastic. The stochastic, the mean is follow the distribution. In such 3 points, I explain some process. The next is some example of queuing model. First is bank. If bank in the bank, the server is clerk and the customer is user. This is, I think it's easily imaginable. And the computer is also the processor is server and program and waiting jobs is customer. It is also easily imaginable. And such as printer and law, this is the same. And airport. And next, I'll introduce one example of an airport of one of the queuing model. This simple diagram of Japanese airport. In Japanese airport, such process is the first. Customer comes entrance. So in this system, entrance is source, but other cutting system, each customer's house is source, I think. This is differ by the this is 日本語で言うと、ここはそのモデルの構成の消し方とか切り方で変わってくると思います。ここはこのソースがエントランスとなるか、それぞれのカスタマーの入れとなるかっていうモデルの切り方によって変わってくると思います。で、カスタマーgenerated customer by the source. First, it goes to this queue customers. This arrow is flow of customers. This is this arrow is arrive system, and this is queue is waiting process, and this check-in desk is service system. This arrow is arrival, and this queue is waiting. This security is service. This is Japanese the diagram. So the next I introduce this model is text one, but this is text model. But I think this diagram is not nearly Japanese diagram because entrance, if customer comes entrance, then information new customer goes to information desk, and then next to check in, and the next is passport check, and then gate A plus U. So, but I think it's not much my knowledge about airport. But this in this text says in this text introduce some this figure. So I explain some. I explain diagram by this one. So, if runs the system, running the airport model, this circle is the first passenger comes. This is the some example of run the simulation by the text. The first, the passenger comes per 1.5 minutes. So 40 passenger comes per 1 hour in this setting. Then next, a customer goes to information. In this information counter, information serve customer per 1 minute. So about 60 customer serve per 1 hour. And then check-in desk. This if customer goes to check in from this place, cost about 5 minutes to 20. So if some customer have the baggage, serving time cost this express is about have a baggage customers. If passenger have some garbage, serve time cost is this. And if not have baggage, serve time cost is 2 to 4 minutes in these steps. And then passport check, sometimes costs 1 to 2 minutes. So in this case, simulate in this case, information desk is 1 and the passport check is 1 and the check-in counter is 7. This content is first class desk is 1 and C class is the main is business class. Business class desk is 2 and Y class is the main economy class. Economy class counter desk is 4. So check-in counter is 7. So in this simulator by this case to check about bottleneck of this system. So I challenged to make this simulation by the source, but
This is why you ask me to how to use the time variable on
So yes.
the weekend.
But I made but is 途中なんだ。So touch. But I finished in this area. So in simulated by in SOAS, the customer moving such as first customer go to this entrance and then go to information and so such as but this is 途中です。in the text, find out some bottlenecks. The bottlenecks is so passport checks because this is passport check to simulate to find out the bottlenecks. So queuing model is to analyze where is the bottleneck. This is the purpose, one purpose of queuing model. Analyze where is the bottleneck. And then I explain some software. So in text simulated by script. And script, but the latest version 2.5 change event-oriented simulation into process-oriented simulation. In text simulation is by the script, but this version is 2.5. So 2.5 is process-oriented simulation. So I think no matter use script or SOAS because not event-oriented. So I use SOAS to make simulation. So yeah, so process-oriented the means regarding and operating the system as the flow of the state transitions. This is process-oriented. This is summary. Queuing model is suitable as like it's attempting to model element in the target system as customer, server, and queue. And server and queue is static object, and the customer is moving dynamic object. And queuing model is available to detect bottleneck and to redesign workflow and business process. And but queuing model have some problem. The model cannot express the adaptive behavior on the part of the customer. Such customer are called dynamic objects, but they do not change their behavior during the simulation. So if some customer change his go to change things about to go to trip. So by some inspiration. If so this this string model have such programs. This is summary. And that's all. There's some comment or question.
So the thing is that for this methodology, like Turing models, we need continuous time, right? But in source, we have only discrete time, right?
Yes.
So how did you do that? How did you try to implement that model in source?
source はイベントとイベント I explain but event oriented simulated I don't know so I my only select is to make some process oriented simulator so I make like that source. Do you know some event-oriented simulator? No.
But most of the simulations I know are like discrete time.
And also discrete time simulator so I don't know event to event simulator.
Also, how would you do it? Like if you want to have to simulate something like discrete time source, what can you do? Continuous time source.
Possible using the computer to make some simulation model. It is impossible to use the continuous time. You can divide into the micro level, but maybe it will be discrete time. Maybe 0.1 second, 0.001 second. You know that long curve simulation long curve simulation. In that system, I think that every agent decides what they do every 1 second. But the point is that the 1 second is exactly 1 second. But in source, maybe you can define the 1 second as a step using the daily counter. But source don't continue simulating. I'm sorry. Source don't continue simulating before all agents decided or stopped. So the 1 second is not exactly 1 second. But in low-cap simulation rig, 1 second, if the agent cannot decide what to do in 1 second, I mean that if you program the wrong code, maybe agent cannot calculate their definition by 1 second. So, but the world continues. And you know that I think almost all simulation language and programming, almost all simulation language uses a discrete time system. because it is hard to maybe represent the continuous time. So the source uses the event description, event-driven style, like stage model. But other simulation language, I think 90% or 95% simulation language don't have this event-driven style. So it's very difficult to change the definition rule. Maybe you can, maybe you will have same problem. Maybe you making the model by Java.
So I understand that in source, you can define the step, say 1 second, and then you define events that are like a multiple this time, like go to this spot and wait here 5, wait here 6 seconds, and after that you can move to do something and then move to another spot. Thank you.
As Mr. Ichikawa said, in text, program code, right, but this is too hard to change, I think. Any comment or question?
In the text, is there any explanation about Poisson distribution? Poisson distribution is a very famous distribution in arriving model.特に使ってないか。いや、だけど。
So, Poisson distribution is such distribution is such a Poisson distribution. So, I made this model use the Poisson distribution touched.
Approximate.
So such. It is often said the distribution of people comes is follow Poisson distribution. So this if so such is such probability is such Poisson distribution.
ポワソン分布わかんないんだったらだそうです。
Poisson分布。Can you explain Poisson distribution?
Discrete distribution. I understand that this is another distribution, but for discrete time. You know that in the classes of
Right. So mathematically, assumption, a strong assumption that every comma have no relation. If every comma customer has no relation, then the distribution of arriving number is followed by Poisson distribution. This is mathematically
Have no relationship.
yes. いや、ゼロはちょっとあ、まあいいのか。あ、いいのか。ゼロと1はゼロは一応あるけども、ピークはどこだっけな。 まあ Google 見るのが一番早いんだけど。要するに何も分かんなかったら、何も過程がなかったらポガソン分布と置くという決まりがある。
So this rate is such as.
これ横にはい。
The Poisson distribution have a parameter lambda. Lambda is average rate of coming customer by step. ラムダがそれ1の時かな。
確率だけでやるの。
全くお互いに関係がないという過程なの。だから実際はそうじゃないんだよね。
Any question for comments?
Not comment, but request for source. I need a Poisson distribution. Are there any possibility to represent the Poisson distribution source?
In the lecture, so I made Poisson distribution module. This is just approximation.
And then one more important thing is that you know that some scientists or some programmers said that the random function in Java is not so good. So there are many algorithms to calculate some random parameter.
Nelson Twister.
Maybe you search in first class. I think the Mr. Sasaki's board there is some function. I don't know where it comes from, but he got some programs, random function, made by Java from I don't know Kobayashi Lab or he got a good function. So you can find it and maybe you can read that code.
How we can evaluate if it's the good algorithm to generate the random variable or it's not good?
I don't know. Ask Kanma-san.
How we can evaluate the effectiveness of our random number generation?
難しい。
Java のランダムって時間でしたっけ？
Java は
時間
初期化は initialization is a time function and this is a old style 線形合同法 linear conjugate.
Maybe in the Java built-in function, in the random function,
Yes.
they build based on the uniform distribution.
Yes.
And also they are in normal distribution. And if we generate two kind of generating number, random number generating by using the same distribution, maybe it is must be same because we generate based on the same distribution like uniform distribution. Also in MATLAB, they also generate the random number by using uniform distribution with A and B parameter interval. But maybe Ichikawa Sensei said their effectiveness not according to the distribution, to the distribution itself, but according to the some kind of we can represent shift to the number and the number is not changed every what time and maybe this is the effectiveness to use different generating number in Java or in some kind of programming language. maybe if the generating number is based on the same distribution, like uniform distribution, maybe the algorithm is not differ from one algorithm to one algorithm. Maybe it is according to the maybe machine the binary number or binary coding of the system. Maybe how we can generate the uniform number of generate random number by using uniform distribution in Java. Maybe it perhaps different to generate by using MATLAB, because the Unicode or the bit he used maybe.
You say you want just as a distribution otherwise by than uniform distribution with person. This is そうか。それはなんだ。For special case, so special case where we need this is mostlyなんとかレシピ、mathematical recipe for Knut's book.
Yes.
いや、ダメだ、難しいな。一応分布から2の分布を作るやり方はかなり宣言されたものがいろいろ昔からあるはずです。それを英語で言いたい。
Swar's random generator is follows Java.
Yes.
Okay.
Practically no problem.
You know that 10 years ago maybe, you know that rand function in C language,
Yes.
it's not so good. And some conference, some software conference said that C-rand function is not so good, so don't use in the model. Because you know that Java's random function is really good, and maybe you can get the various parameters. But in C language, rand function, maybe 1, 2, 3, 1, 2, 3, 4.
String related to multi-dimensional.
Yes.
And lower bit distribution
Lower,
is
yes,
very bad.
By the way, you know that swords can use the same seed to use the randomness.
Same seed. So the only four seed we define.
Yeah, you can get the same again.
This point is, I think, this point is lecture on the Swar's seminar. So my presentation is in.
By the way, would you give example of last in first out?
Last in first out? オートマタ。プッシュダウンオートマタ。
Yeah, I know that, but example in the real world. Maybe you give us the example of first in first out using the air code model.
ないよ。
なんだろう、last in first out。なんか自動案内機って
まあ本当はそれはまあ抽象的にあれだよね。
マニュアルがあるの。ありますか。自動販売機ってラストインファーストアウト後ろから入ってきますよね。
イベントになってるジョブとか、そう特殊な状況で細長い倉庫にこう物を出し入れする。
自分らってファーストインファーストって何？
小森君、
自分来てファーストインファーストって何？
多分上から入れたら下から
出てますよね。
多分だからオートマトンの話じゃない。私が本当わかんない。
シュランオートマトンのその
古い商品がずっと残っちゃうと思います。
してくれたのが、
そっか。
あれかな。紹介状を持った患者が。
ああ、それはでも飛ばす優先まあなんだろう。
最後に言って最初に出てくる。
商品棚で上から上から補給して上から買われる。
平積み。
平積みの方。
ファーストインラストアウトか。
ブックシェセラ
その
ブック
Looks last, maybe
ス
you
タッフ
can
のブック。
newest one in the top, but last to this. So last in first out.
The bottom of the stack is very very old.
飛び箱並べるとき片付ける
でも間違いでつないでしょ。
そうだ確かに
預けてもらうのを待ってる。
源泉かけ流しの森でこういう下からじゃなくて溢れてくやつ。絶対に下の方は溢れて温泉の
コンビニのおでん。
あ商品棚って結構そうですよね。
多分入れ替えないと。
今禁止されちゃいましたね。
商品だか。
コンビニの弁当とか
昔は新しいものが前に来てた。あれは禁止されたでしょ。ちゃんと後ろから並べなさいってこと。
コンビニ後ろからそうです。
なんか一時期そういうのが推奨されたみたいに書いてありました。
問題になった。
Okay. So, hello everybody. Today we'll be talking about multi-level simulation models. So, the talk will be So I will be talking first about some theoretical aspects and later I will introduce some practical examples. So first I will talk about, I will make a summary of the approach and take an example from the field of synergetics about opinion formation. And then in the practical part I will talk first about a software called most language, I don't know how to read it. Then I will show you 3 examples. One on opinion formation, gender segregation, and we will review the model called Lab Idol, which was exposed by Madahazari. So, a brief summary of the approach. Well, I will take an example with a population of individuals. In this model, individuals are born and also they die according to some rate. Here, birth rate and death rate. Also, the individuals have some attributes. The blue ones are male, the pink ones are female, and well, some of them are dead, are already dead. The thing is that this is a closed environment. So, if there are many people, this parameter will change. Like, if there is too much people, there will be enough food for everybody, and some people will die. Right? The death rate will increase. So, we will consider this typical case. When we have a multi-level simulation setup, we have typically a population with its attributes. In this case, we have the population which attributes are size, so it's right here, birth rate and death rate. And then we have that population is composed by many individuals, which are also agents, and each individual has its own attributes. In this case, I consider two, only the gender, the sex, and also if it is already there or not. And the characteristic of multi-level simulation is that we have that the attributes of the population depends on the attributes of all the agents it contains, and at the same time the attributes of each agent depends on the attributes of the whole population. There is a feedback between the macro level and the micro level. So that's the main characteristic of multi-level simulation. How does it apply here? We have that the fact that each individual is dead or not is affected by the death rate. Like if the death rate is low, the probability of this individual making the transition from life to death is low. But at the same time, this death rate depends on the size of the population. And the size of the population itself is it depends on the aggregation of all the individuals. So there's a loop. Okay, so that's the main problem of multi-level simulation. So there is the problem that, well, if the agent depends on the population, and the population depends on the agent, how do you solve it? And how do you calculate? What do you calculate first? So what you do is the following. We have cyclic dependence. So where the attributes of the population are calculated based on the current attributes of the individuals, like this, right? But the attributes of that the individual use are based on the attributes of the population in the previous step, like this. So the individual used the state of the population in the previous state, while the population uses the state of the individual in its current state. So that's what you do to avoid like cyclic dependence. So what's the difference with microsimulation? Like in microsimulation, microanalytical simulation, we also have like many individuals, and we also have some aggregate attributes. So what's the difference? What's new here? The thing is that we talk about macro policies. Like after in microsimulation, you take the behavior of each one of the agents, and you just aggregate that, and then you create the macro level. But then you don't use that to control the behavior of each agent. Like in microsimulation, there is one-way communication between the micro level to the aggregate level. But once you are in the aggregate level, you don't use that for anything. But here, in multi-level simulation, you use the aggregate attributes to control the behavior of each individual. So that's the point, the novelty that introduced multi-level simulation. Okay, so here I talk about some limitations. So, the thing is that we aggregate individuals so that individuals can, the behavior of each individual affects the behavior of the whole population. That's simple. But what that implies also is that we cannot do the following. In many models, you require like some kind of locality so that this individual will affect not the whole population but just a few of the neighbors, or that your individuals are in some kind of network, and so you need to define that this individual communicates with these 6 neighbors. So you need some kind of local interaction in some models. You cannot do that with multi-level simulation. Multi-level simulation is not that good. In multi-level simulation, you communicate from the individual to the aggregate environment, and the aggregate environment communicates to all the agents. So this is not possible, right? This is also not possible. So that's one of the limitations. Well, now I will Kokumari go. How is it so far?
If express some difference of some
all the time. In these models, all the examples I saw use discrete time, and all the there are no events. Like every step of the simulation, all the agents do the same. Right? There is nothing like a process that takes several periods. No. Well, sometimes you can do like assume that there is a transition to one state, and then the agent will stay in that state for several periods. That's possible to do. Okay, I will show you one example later.
Can you get to the cases? No. Yes. Micro simulation is static, but if we refer to the yes.
Oh yeah, that's a good point. We talk here when I talk about static, means that I'm talking about macro policies. For instance, what we are saying here is that you aggregate the data of the individuals to get some aggregate, but then with that aggregate, you don't use it to control the individuals. So these policies are static. In the case of my initial example, we would consider that we have a death rate, and that rate does not depend on the population. It's static from the beginning. Maybe you can be changed by the experimenter, right? Like external, but it doesn't depend on the population in micro simulation. In multi-level simulation, there is this feedback from micro level to macro level and back to level. So that's the key definition.
So the static in terms of macro level, connectedness between macro level and micro level.
Exactly. Any other question or suggestion? Comment? Let's go. So I will introduce an example from the field of synergetics. So first I talk about the field of synergetics. Actually, I didn't get much information, so this is what I got. This is an interdisciplinary field of research which is concerned with the cooperation of individual parts of a system that uses microscopic, spatial, temporal, and outputs and output structures. Basically, what I understand from this is that this field deals with the concept of emergence. Like you have many individuals that do a task together, and then you have the whole result cannot be explained by looking at each individual. By the way, the word synergetics comes from the word synergy. And basically, it is usually defined as this the whole is greater than the sum. So it says the whole is greater than the sum of the parts. Basically, it means that the system, the set, has some properties that cannot be derived from each one of the individuals. So that is what this field studies. In many fields, chemistry, physics, biology, and a little bit of sociology. So if we go back to the map that we saw in the first chapter, we are here. Like in the 70s, we are talking about synergetics, and when we talk about synergetics, we are talking about analytical systems, like no synergetics. So we are synergetics. We talk about now, right? And then from this, we will in the simulation we will go a step further to multi-level modeling. Okay. So here we go with the example. Opinion from research. So we have a very simple setup in which we have a population of individuals who have to decide over some issue. Should we build another nuclear plant or not? I don't know. Should we increase the money allowance for families who have kids? Some people say yes, some people say no. Right. So we have this following simulation. We have an initial setup in which there is almost a tie, like almost 50%. It can be perfectly okay, 50-50, right? So that's the initial step. No majority, right? And then we have the following dynamics. Each individual has its own preference, but each individual is also allowed to change his decision based on the influence of other people. So if I think like, for instance, I think it's a good idea to build another plant, another nuclear plant close to Fukushima to replace it. But everybody here thinks that it's a bad idea. Maybe I reconsider my decision and I think, maybe it's a bad idea. And then I decide to say no. Well, so, and based on that simple dynamics, there is a counterintuitive result. Like, even though we start with almost no majority, 50%, we get the result after several steps of this game. And after we consider several periods of time, is that there is a strong majority, either rejecting the proposal or either accepting it. So how does it happen? We have the following way to state the transition probabilities. This is the transition probabilities from a person who currently says no to a person who says yes. And it depends on the following parameters. This V will mean flexibility. So if it is higher, both probabilities will be higher. So, but also the probability of going from no to yes will be higher, and also the probability of going from yes to no will be higher, right? Then we have this pi. Pi means here the individual preference for the simulations we will perform later in the analytical results, we will assume that preference is zero. People actually do not care about it. So we can, if we just make that assumption, we can focus only on the effects of this part, which is, well, this part is made composed by two terms, k and x. X is the, it represents which term, has the majority, yes or no. So this is the number of people to say yes, the number of people to say no. And if you make this formula, you will realize that this value is between -1. This value is between -1 and 1, right? Where -1 means that everybody says no, and 1 says everybody says yes, right? So, and that majority is multiplied by this parameter k, which is the most important parameter in this model. This parameter is called Goldwing parameter, and basically it measures, or it represents how strongly people is affected by other people's attitudes, other people's opinion. So, what we have is the following. First, in the fields of synergetics, they approach this program using the analytical solution, looking for an analytical solution, and they did the following. They assume that they measure, this is the probability of an individual saying yes at any time, and they consider a very short period of time, so that at most one individual will change its opinion. So maybe one individual who was saying yes, say no, or maybe one individual that was saying no, now say yes, or maybe nothing happens in that period of time. Just consider a short period of time, right? And there is some analytical derivation in the group, and what we get after we solve it analytically or numerically is the following. This is the So this is the result when we consider a low value of k, a low value of the Goldwing parameter. So this is the time, so that means that this is the initial condition and this is the final condition. And this is the probability of this percentage of the population saying yes. So at the beginning we mean very close to 50%. And when we have low value of k, that state remains for many years, right? But if we have a higher value of k, after some time, we say that the population, the distribution became bimodal. So, at the last step, there are two options. Either most of the people is saying no, that means the percentage of people saying yes is very few, very little, or most of the people is saying yes. But the probability of staying in the intermediate state of like a time is very low. Any questions so far?
Excuse me. What is flexibility? Flexibility.
This one?
Flexibility.
Flexibility. Right. The thing is that we have this parameter measures. Basically, this parameter affects both probability. So, if we increase this parameter, both probabilities will rise. Like people will change their mind more often. If the flexibility parameter is high. But if it is low, people will be like stubborn and they will remain in the same decision for a long time.
And coupling is different from flexibility.
Because this one basically affects both probabilities. But this one affect how people will try to, how people is affected by the majority. So, for instance, if the population, if most of the population is saying yes, this coupling makes that this transition from no to yes is higher because a lot of people is saying yes, but this transition is lower, right? Because if everybody is saying no, the probability of going from yes to no is low. The coupling is high, right? But if we increase the flexibility parameter, both populations increase, both probabilities increase, regardless of the state of the population.
Can I ask why is minus k? Why?
No, yeah, tell me.
Yeah, but I think if in this case the meaning of k is the same because for the no to yes you use plus, right? But for the yes to no you use minus. So k is the same. So if you know what I mean? Yeah. But the formula is different.
The real formula is different. Oh my god.
Same as text. Sign.
Here we go. No.
6.1.
Yeah. It's
If x is 1,
This one is okay.
it's likely to.
It is okay, right?
If x is 1, it is likely to change no to yes and
Yeah. Like the question is why here k has a positive sign and here a negative sign, right?
no, I mean because previously you explained that k is different for yes to no and no to yes, but
Like the value is the same, but
yeah.
the influence is different.
oh yes,
Right?
misunderstanding.
Because it's multiplied by the probability.
Thanks. Yeah.
Okay, so that was the example. Okay, this is what you do when you solve it numerically. So here's the point. Now you take the same model and you implement it in the software the book is exposed. The software is called Mimose or Mimose, I don't know how to read it. So actually it comes from German, so no idea. So it says it's for Linux and there is like a server and a client. It's kind of sophisticated. Yeah. The code looks easy to understand and also it offers some diagrams. The thing is that I was too lazy to download it and try to make it work in Mac, and it's a little bit old. So what I did was the following. So he used Stella and Comunicon used SARS. I will use Excel. Okay, so this is what I did. Like basically, I use the same parameters of the group. I have a. This is easy to read. So for the kappa, I mean the k, the coupling parameter, this is the value, and I have to find this value for the parameter by myself. So basically, first we consider the attributes of the population. So we consider the attribute of the population is the x value, like the majority value, and when we consider each agent, we consider the value of each agent is it's both. 1 means yes, 0 means no. And well, I initialize this at time 0 randomly, and for each period, basically, you take the probability, this probability transition thing, the probability of going from no to yes, and yes to no. That probability, according to this formula, according to this formula, that transition probability depends on the preference parameter, right? So each agent has its own preference, so it should be different for each agent. But in our case, we consider this to be 0, like no specific preference. So that probability transition is the same for all the agents. So I calculated them at the level of the population. Well, I will send you the Excel file later if you want to check the formula. But basically, it's an implementation of this idea. And we use these probabilities to define at the level of each agent if they decide to switch from yes to no or no to yes. And what we obtain from the behavior of the average is the following. Usually, we begin close to 0 because 0 means like no majority, and it quickly moves to one of the extremes, either yes or, in this case, it is close to 0.5. It's moving closer to the yes. Calculate. So we run another simulation, and then here it begins from close to 0, then tries to go up, down, and then finally goes up. So if I change some of the parameters, I will make it a little bit more sensitive. So in this case, I made run it several times, and it moves to one of the extremes more closely, more faster, right? Faster. It's on. Inclusive, and it moves very close to one of the extremes. So a majority is formed very quickly if I increase the beta. Okay, so we can play with this model like if we choose a lower value for kappa, it will remain close to the mean value. And if we make several simulations with the same parameters, we can try to obtain the distribution that we saw in the case of the numerical simulation. I tried to do it here, but I did it with a very low value for B. So from the middle, most of the time the model starts close to 0, and it moves to one of the extremes, either to everybody saying yes or everybody saying no. But for these parameters, they move too slowly. So maybe I need more iterations to show that they all converge to either everybody saying yes or everybody saying no. So that's why you should use a proper simulation. For instance, the formula is simple and it's easy to simulate it in Excel. Like if you want to test it manually. But if you want to make like several experiments or change parameters, it is not a good idea to make it in Excel. For instance, I use 100 agents. So somebody asked me, hey, what happens if you use 1,000? If you use a good language, you can just change one number and run the simulations again. Here I have to change all the formulas. But anyway, it was fun. Usually, like, if you have a good idea of a model, you can build like a toy model, like with just a few number of agents and build it in Excel and see if it works. And then after that, we try to build the whole thing real simulation language and run the whole experiments. So I think Excel is usually like a good idea for a first approach. Any questions so far?
Yes, Masan.
Hi.
In this formula use exponential function
Yeah.
to express the probability, transition probability.
Yeah.
One, we may consider the exponential.
How many people see that there is a big problem with this formula? You think it's a probability. It measures a probability. What problem does this formula have?
If we use exponential to make the probability, the exponential say that mathematically we have the positive value. This is according to the probability value between 0 and 1. And my question is, if we change the exponential function to the function with the same property, it is not lie between 0 and 1.
Well, I understand. Maybe you think that if we just put some value here, this result may be 2.7, 10. Yeah, but this is not a good expression for a probability because it can be more than 1. Actually, if you put these two parameters high enough, the model will oscillate between yes and no continuously. So basically, what you do to calibrate this model is you find a nice value for the k that you want to measure, and then you find a value for v so that it actually represents a probability distribution, so that this probability will be between 0 and 1. I have to do that like after setting this parameter, try to find a good value for v. It is not written with it.
But in this model, the simulation assume high value is 0. Yes?
Yeah.
Why?
Because it's even a more interesting case. You have maybe you have a lot of people and nobody really cares about that stuff. They say never mind, if everybody say if people like it, it's fine. If people don't like it, it's fine. They don't have a personal preference for any outcome. But you consider only this effect, the effect of being influenced by other people in the situation. And you see that a strong majority emerges, everybody saying yes, or everybody saying no.
But in reality, we have our preference.
Yeah. You can do that also, try to put some preference and see.
It is difficult to include the parameter I in this model.
No, it's very easy to do. The parameter is in the model, but for the experiments, we drop it.
But if we have 1,000 agents, each agent have different high value.
Yeah, it depends on you as an experimenter, mentor set that what you want for me. I think that I didn't try it, but I think that even if the population has a slight preference, for instance, the preference for yes is higher than the preference for no in the population. But due to the interaction between people, may be a strong preference for no emerges. So that's a possibility in this model. And that makes it interesting. Even though if you ask every people for its own interest in each one would say yes, I prefer to say yes. But due to this interaction, the outcome may be everybody saying no. So the first example in the book is the following: opinion formation, but in this case they implemented with the software with Mosaic and with these parameters, and I try to do the same. Basically, here this is the initial value, and in most of the cases it leads either to 1 or to 0. And very few runs of the simulation remain close to the middle. It's basically the same result I obtained with the example. So this is the second example, which is more interesting, which is about gender segregation in schools. Like, like there are some schools that are only for boys, and then there are some schools that are only for girls, and there are some schools that are like co-education, mixed. And in our second example, we consider the following scenario. There was a process in Germany in which just after the war, there were a strong segregation in schools. There were a lot of schools only for boys, only for girls, and very few co-education schools. About this, in the 50s we had like the number of single-sex schools were slightly higher than co-educational schools. And 40 years later, that number decreased strongly, and now they have much more co-educational schools. So the question is how that process happened and the role of the government in that process. But although this refers to people to kids going to school, the process they study is the following. They analyze the behavior of the process of assigning teachers to the schools. And the observation is the following. Same-sex teachers were in a large majority in single-sex schools. That means that if you have a school for boys, most of the teachers will be male. If you have a school for ladies, for girls, most of the teachers will be female. So what they did was try to change this fact, try to assign female teachers to male school and also male teachers to female schools. So this is what we will know. So they take data from this place, from Rhineland-Palatinate, at the south of Germany, so here is Germany, the European Union, we are close to the south, and this place is famous for castles. Right? So actually, in Germany, there are castles everywhere. And these are very beautiful. Back to the example. So they assume the following. To recreate that process and that data, they have 3 assumptions. First, that when a teacher leaves its work, well, it has to be replaced, right? So the probability of being replaced by a man or a woman is equal. Second, and the second element of the model is that men stay in their work twice as long as women. They don't explain why, but I assume it's something related to maternity. Maybe women get pregnant and devote themselves to their field. But well, this is just a fact. And the third element is the way the new women are assigned to schools, depending on the preference of the school. And we consider the following probability. We have a probability of assigning a woman to a school that depends on the percentage of women in that school and preference factor by each school. This preference is the preference of the school. Yeah. That means if that value is high, we have the following. High K means high kappa means high preference for women to be sent to schools with a high percentage of female teachers. While K equals 0 means there is no such preference. So if we consider kappa close to 0, that means like even if it is a male school or a boys school or a girls school, they don't care. Give me I need a teacher, send me a female teacher, or send me a male teacher. It's the same. If kappa is close to 0, but if kappa has a high value, they prefer same-sex professors.
Guy means proportion of woman means the teacher.
Yeah, woman teacher.
Not means student.
Very good question. No students. We are talking about professors here. Although they assume that the proportion of the female professors affects the proportion of the students or women students in the school. I tried to find more about that relation between the percentage of professors and the percentage of students, but it's from a paper in German. So I found a link to the paper, but it was in German. So sorry about that. Okay. Any other question about this formula? Okay. There is some interesting fact here. Like, just imagine that this value is high, and that you need to replace some 2 female teachers, right? So we say that means that they prefer to be sent female teachers, right? But we also say that in general, the probability of sending a man or a woman as a teacher is the same. That was a policy of the government. So how they did control that? They control that with this term, with this probability. This V is used to more normalize this probability, so that in average you send in total the same number of male professor and female professor teachers. So here we go. So this is a 3-level simulation model in which we will simulate a state, which is an agent, but at the same is composed or contains many schools, which are also agents, which at the same time contains many teachers, which are also agents. So we have this, we have a state which has a list of schools which manage this probability with this value to control that you assign same number of male teachers and female teachers. And it has this value, which means how many teachers are required in every period. We have schools which has a list of teachers, which have an attribute which is sex ratio, this probability, and the type of school. Co-educational or single sex. And you have teachers. We have age, sex, and duration of contract. Duration of contract is important because, like we may have shorter contract, but they stay shorter in their job. So it happens like this. This probability is affected by how many teachers. Okay, so based in this probability, each school decides how many teachers required, right? So this affects this probability of the state, and which at the same time affects this control parameter, and that feedbacks to the probability, right? So that to assure that you assign same number of men and women. At the same time, this probability also affects the sex of the new teachers. And that sex affects the sex ratio of the population of the school, which affects again this probability. And this thing the teacher required is also to by this the duration of the contract of each teacher. So what we have here is we have like 3 levels and several feedback mechanisms between them. Like to understand this more like precisely, you have to look at the code of how they implement. But I think the idea is not good. So what they did was they coded it in 9 months. They calibrated it with real data from this province in Germany. And the data is as follows. The average contract for men was 30 years, for women 15. And regarding the schools, initially we had like 45 schools for girls, 45 schools mixed, and 60 schools for boys. And the total number of teachers was somewhat proportional, right? And also this percentage of women teachers was taken from real data. And what they get was the following. Like in the left, you have the evolution of the real historical data, where you have like this probability distribution. This measures the probability of a percentage of women in a school. So either you have a lot of women teachers, most of women teachers, or you have very low, like no the intermediate values. And what you have when you consider the time is that 40 years later, the population becomes unimodal, like at the beginning was unimodal. Okay, so we have that from real data. So they ran the simulation with the parameters I showed before, and they got this result. And what they say is that this simple simulation with those parameters and with that simple rules for acquisitions of new teachers recreates the dynamics of the original data quite well. As far as I understand, these results were used somehow to support what is called a positive discrimination of like the government took a role to make this happen. It didn't happen alone. But the main message of this simulation was that even if the government had this policy 40 years ago, the results, they have to wait 40 years to see the results, to see that the increase in pre-educational schools and mixed education. Any questions so far? So I continue. So the third example is the dog law by the model institute, and they did this modification. Like instead, when we consider system dynamics, we consider 3 populations increasing or decreasing in size. What we consider here is we have only 1 population, but each agent has 1 attribute, the kind of strategy they are using to play. If they are playing like a hawk, playing like a dog, playing like a dog, law value. And the transition probabilities between each kind of strategy depends proportionally to the reward of each one of the strategies. These are the formula. I will not go into detail, but you can check it in the book. And they implement it in Mosa again, and then they create this graph which is very similar to the one obtained with system dynamics. Quite interesting. I think I can do this one in Excel too. Okay. And that was all I have to say today. So, questions, comments, suggestions?
everybody's hungry.
Thank you very much for your attention.
Great presentation. Thank you. About today's seminar's feedback sheet. Sorry, I'm making it. Maybe I will send the email 1 hour later. Please entry the feedback sheet.
Maybe the feedback sheet is based on my previous, because the presentation is the same group, to the second group. So I have already sent the so maybe the form can be used.
Next seminar is next seminar is June 15th. Next week is nothing. Next seminar, the chairman is Mr. Yakisawa. And presenter is Group 3. Next seminar, the chairman is undefined. Undecided. 誰にしましょう。じゃあ、ミスターマヤ。OK。何かアナウンス。掃除の時間。
掃除は1時半からでいいでしょうか。
1時半。
1時半で。
今日買い出しあります。
お願いします。
あと、金曜日にもゴミ出しをしようと思って、で、出血の表の左側にマグネットをつけるんで、それを見て、ついてる人は金曜日にゴミ出してください。
黄色いやつですか。
で、やった人がマグネットを下に順番にローテーションをしてください。
一人ですか？
あ、1人か2人で。多かったら2人で行ってもいいし。2人いったら、
マグネットは2つついてるってことですか？
いや、1つだけど、2人で行ったら2つずらしてくる。
あ、わかりました。マグネットのところから下2つが、それとも下1つの人が一緒
1人で行けそうだったら行っちゃってもいいし、2人がよかったら2人で行ってもいいし、お任せします。って感じでお願いします。金曜日。
他に何か。
仮鉄の、行く方法とあれは教員として知っとかなきゃいけないので、事故あると困る。
木曜日ですね。
いや、どうなってるの？
特に
事故とか、こっちが困るから。
人数が多い。
本的にはみんな電車で行くんですか？なんか
俺的じゃないで
そんなにみんな一緒に行けるような手段はない。
そういう車で行く人はいないよね。
そうです。
バイクもない。
何
行き方わからない。
じゃあそれは Ask Google。
じゃあ一緒に行きましょう。
そう。基本的には電車です。
長沼駅からここまでのどのぐらいかかるか。
電車なの？
あ、でも
何か他の手段でいいっていう方が。
一応さ、参考までに言うけど、去年ね、僕以外は送ってもらうって言いました。
駅から
駅から
あ、前からだって
何
駅から遠いんだよ。
あ、そうそうそう。結構
長沼
1キ
じゃない
ロぐらい遡る。
駅
1キロだったら
1キロぐらい遡る。その北野って駅が多分一番近い。そこから北野の駅から
でも
1キロぐらい
八王子からもバス出てるんで。
ああ、なるほ
ただそのバスもこんな感じなんで、一つが送っているのことを知る
何？
っていうのが去年。
こんなにたくさんいますよ。
無理だね。
無理ですね。
M1 の金曜日の午前の送りはやるけど、しょうがないかな。
お願いします。
あとピストン運動するしかないのかしら。バスだっけ？バスないんだよね。
バスないですよ、あそこ。
ないんですか？八王子からも
あるけど、
本数が少ないってことですか？今減ってんのかな。あ、そうだけど。
それさ、Google マップ出してみて。場所。一番危険なのこの辺でしょ。行ったことない分でしょ。
どうしよう。やろうか。
で、マヤ君さ、資料の受け渡しってどうなってるの？タレツの。多分メールじゃ送れない量でしょ。だって今度の月曜日に提出になってるでしょ。タレツの発表資料。それを研究室内で配んなきゃいけないから、多分メールじゃ添付できない重さのはず。
じゃあそれも
ファーストクラス。ファーストクラスかな。
そうする。
いや、ファーストクラスでいいですよ。
そっち2時だね。
表示されてる。
じゃあ2時で。
どうしよう。私やろうか。
じゃあ、
こっちダメなの？それが変わる可能性がある。
集合何時だっけ？確か2時半。2時半か。1時頃。
よっ。
サイエンス。
モルコーキル。
どうして
科学哲学全部場所本当にすごい建物ですか？八王子セミナーハウスってすごい建物ですか？見た目
汚いってこと？
いや、なんか
車じゃないよ。
なんか突飛な形をしてますわ。
車で行くと気持ちいい。
これですか？
家族で
あ、これ
すごい形をしてる。
あるかどこからか知らない。セミナーハウスの八
八王子と北野と南大
すげえ、素泊まり2800円です。
でも二度の口とかこっちから行くんだったら八王子
みんな
から行く
iPhone でちゃんと入れて歩いてきて。
これが住所。
ナビウォーク。一緒に行けばいい
僕の午前中って授業だっ
まあ木曜日はないです。
け？じゃあみんな直行なのね、家から。
チャンさんと関さんは
来たのって
どうやって行くんですか？
Are there any appointments on next Thursday morning?
Yes.
So everybody go to the Hachoji seminar house from your home right? You know that we have to be there at 2:30. 合ってる？
はい
2時半だって 2:30. And みんなデートしてる。
見ちゃいます。
ああ、覚え
あ
横浜。
あ、どうですか。
みんなあれかな、横浜線が近いから一番鳥がいてみた。
近い。
八王子駅は
京王線と浜線、横浜線で横浜線が近い人。
よく同じはず。
片倉、去年片倉でしたっけ？
かな。
一番近いんです。
めっちゃかかんだよな、このピストン運動。八王子南尾ですよね。多分これでこのバイパス使いましたね、確か。
で、そっか。
これですよね。このバイパス使ったんですよね、この間。多分。
多分、これじゃないかな。
じゃあここだ。ここに
八王子
1時。1回往復30分でしょ。2回で1時間。1時だな。
八王子南の。
に1時。カンマさん大丈夫ですか？
私はまあ多分。
就是那天那个搜索。
1 o'clock。八王子南の。And there are maybe two cars. Tanuma-san's one, my car. So we like this 2 times. Maybe we can take all of you to the here. But maybe it takes about 15 minutes to from Hachiyoji Minamino to Hachiyoji Seminar House. So maybe some people stay here about 30 minutes more.
The thing is that I made the same mistake for 2 years, so I want to take everybody. Usually you take the train like at 11, so you say later I will buy something. But then you arrive to that place, and in that place there is no restaurant. So you can buy like cup ramen, but it's not good. So think about that. Bring your own thing to eat when you arrive to the place, or eat before going. Yeah, I made the same
何に
mistake.
もないよね。
八王子南なんもないんでした。
何もないよね。
去年あれしたとこ八王子南ですか。
そう。
じゃあ、
And also there is no restaurant around here. So first option, maybe you should buy
ファミリーマート
ファミリーマート here.
モデルも一緒じゃん。
アクロスモール何もないんだっけ？
わかんない。この中にあるかもしれない。
あ、マックス、モス
いやいや、1時南の。OK。 で俺送れるの。
which side?
こっちこっちこっち。
こっちあ、こっちは辛いんだよ。
セームクラスに。
そうか。ここのロータリー使えないんだよね。
大丈夫です。通り少ないんで。
確かこここれで日差し強かったからこの下で待ってて。
タオルはないんだよね。ゼミ係いつもは連絡しねえんだよ。なんだっけ、タオルはもう各地だって。
ノーアメニティ？
ノーアメニティ。ノーアメニティ。
タオル。
No towel, no bath towel, no toothbrush. So you have to bring them by yourself. Okay, don't think that the Hachou seminar is not hotel. Like a youth hostel.
But it has, we have lunch and
Yeah, it's dinner. Because there is a
いつまでにや
restaurant.
ればいいんですか？
but not the perfect. We cannot buy food.
じゃあシャンプーとかも持ってった方がいいですか？
ジムのシャワー室とこういうのがあると思ってたらいいと思う。レストランだもん。あとね、寒いかもしれない。あと虫がいっぱい。There are a lot of insects. Maybe if you have a camera, maybe you can bring them, take a look. そんなもんでしたっけ？
今年はサッカーないのかな。
いやですもん、ああいうの。ワイヤレスはあるけど、つなげません。みんな内職するからダメ。あとなんかある？ Any questions?
泊まる場所をしよう。
知らん。あと俺が知ってんの。さ、ゼミ学科にさ、そことそこなんだけどさ、インサイドデグラブのさ、八王子セミナーの注意事項にちゃんと書いてるけど、そしたらもうアナウンスする必要ないから。
はい。
昼ご飯気をつけるとか、アメニティはなしとか。あと、もう一個ですね。Maybe Maya can will upload the materials and the presentation file or groups material file, presentation file to the first class maybe next month. You know that the deadline is next Monday. Huh?
The material for
Yeah, science philosophy seminar. Maybe you heard that the deadline is Monday, next Monday. もうやってるよね。
あ、そうです。3
Sunday? I don't know, but yeah. 日曜日？
多分
じゃあ日曜日だね。So Maya kun will get all materials and he will upload them. So be sure to download all materials to your laptop, or maybe you can print it out. If you, my recommend is that maybe you should print out the material, because that's the, that science philosophy seminar is for studying the science philosophy. Maybe in studying, just seeing the materials by your laptop, you cannot write down the memos. Maybe you should write some memos or annotation directly to the presentation file. I mean the printed out paper.
Everyone's presentation material.
Do you know how many presentation? How many member?
Maybe that, that maybe if you can remember all things talking in the science philosophy seminar, you don't need to print out. But the study is using the brain for studying it's a little bit different from some discussion, taking a memos or notes. So maybe you want to study, you should print out some materials. If you have the iPad, maybe you can put the materials there, and there are some applications which you can write down the memos, like Mujirushi Note or I Annotate. I always use that kind of application. So I always writing the memos to the iPad, maybe direct to the PDF. Or using the Adobe Reader, there are some function to put some memo or annotation.
リーダーでもできる。
リーダーできます、コメント。So you can put some comments to the slide or presentation bar. So maybe I don't mind that which way you take, but if you are a kind of analog people, maybe you can print out. But the point is just open your laptop, seeing that hearing is not so good. Maybe you cannot understand everything. Maybe paper materials, the first step. If you have an iPad or like that, maybe you can use that. And maybe you are digital people, maybe see some materials to the laptop and type into the notes there. It's fine.
これがいいと思う。タブレット。It means タブレット。
日本語の勉強。And I have one more, maybe 5 minutes. You know the cloud disk? Maybe all of you heard the word cloud. Cloud disk, like mobile me, Dropbox, Sugar Sync, like that. First class has also the same function. But I think all of you don't know how to use that. So in the Windows user, okay, for Windows user, click here. The win. And right click. Computer. Right click. Okay, then 追加はね、I don't know Windows this. Please switch to Windows 7.
No, I don't. Anyone use? 社員誰かセブンない
多分ですね。追加はないです。
ない
同じです。
同じない
コンピューターにネットワークの追加ってない？
ないです。
ネットワークドライブ。
ドライブの割り当てじゃないよな
俺？
嘘やしね
なんでさっきより俺だよ、八木沢君がうまくいったぞ。
これじゃなくてこれでいきなり帰っちゃうん
それ
だね
でいいや、ネットワークドライブの割り当てでいいよ。
じゃあ Z でいいかな
で、http://fc.cs タイトル
受け付けるかな FCDIS? あ
CS
CS
DIS タイトル ACJP スラッシュキャピタル L OGIN ログインスモール
これで OK?
And the username is the same as the first class username and password same.
最初にですね。
見えたすごい
You know, maybe these folders are like the icon in first class layout. And in the file storage here, you can use the file storage like cloud disks. So, like Dropbox or Sugar Sync. And there is no limitation. You can put 10 gigabyte file. You know that the first class has 1 terabyte. So you can use this as your cloud disk.
This is not shared
Not share.
your private.
private use.
What about time capsule used for our recaps?
Time capsule is only for only the backup.
Because that's
Yeah, I have
what
to.
we are using.
Would you log in by client software?
入れない。
ここから
You know, the file storage is same. But there's no, maybe you can find make a new folder, maybe. I don't care.
うわ、なんだこれ。これ。
Yeah, use the English. And check this. Maybe you should upload that. So you can use this one as
Synchronize.
cloud disk. 何をやってるかわかんない人はクラウドディスクを勉強するんです。マナハン宇宙ネクトゥわかった Windows のクラウド
これって一回追加したら
コンピューターにあるはずのちょっとコンピューター出してもらっていいですかこれで Z がもうここに来てるから、あとはネットにさえつながってれば
ログオン時に再接続をチェックしとかないと次消えちゃうから。
ログイン再接続
なんだっけ。
これの右クリックでいかないですか
というか、ライブの割れてる時にこれをつけとかないと次消えちゃうから。
はい。ついてました。これ。
つけたはず
あ、じゃあ大丈夫。
なので、これでとりあえずファーストクラジョン上にはデータを置いとけるので、ちょっと同期っていう素晴らしい機能はないんだけれど、ネットにさえつながっていればここにはデータ取れるので、あとは、例えば自分で同期ソフトを入れるとかね、A というフォルダと B というフォルダを同期取ってくるやつがあるんだけど、そういうのをうまく使うと、さっきのクラウドのディスクと自分の例えば研究用のフォルダを同期取っちゃえば常に新しいものがそこにあるから、例えば家にパソコンがある場合は研究室にパソコンを置いてって家に帰ったらネットワークにつけてこれデータ取れば全部マッチング取れるよね、同期取れる。で、for Mac user, check the Finder is now active. Maybe you just click the desktop and then go 接続ね、日本語の to the server, connect to server. Just same HTTP from slash no not slash fc.cs fc.cs fc.cs.dis 書いて.acjk スラッシュcapital L login small o gin スラッシュMaybe you should do. Yeah. Sleep favorite servers. Then after that connect to the answer. So here is the username for the first class and the password. Maybe
We need the same of our Facebook and first class.
yeah, first class, yeah. You should. You can connect to the first. Maybe the username is different. You might have all nine. See.
ファイルストレージは日本語だ。
Maybe Manahan can read this. File storage here. If you double click, maybeないな。なんもないな。入ってない。会議室。
あ、でもなんか他のところのフォルダが見えない。
いや、ないの、フォルダが。出口研究室。あ、ないんだ、フォルダが。
ファイルがある。
自分のフォルダに行っても別に。
そう、これだけだね、これ。ファイルストレージを使ってください。You can use the file storage as a cloud disk. There is no limitation.
ファイルストレージに入れる。
300もつながんないで数で。そうだでしょ。これ、メール違うでしょ。自分で変えたパスワードのはずで。変えてなければ名字になってるから。違うの。何したの？いや
今空き領域とか関係ない。
ワイヤー11とか。
それユーザー
知らない。
じゃあこれを
先生、ログインの HTTP からログインまでやった後、Windows だと参照をすればいいんですか？
うん、多分。Windows わかんねえ。
参照で、
田沼さん聞いて。
どのネットワークを選択すれば
いや、それ意味は出ないな。それ意味は出ない。
それで完了する。
これで、これで OK なは
田沼さん、ファイルストレージのパスって何
そういうのなかったんですよ。
これはあれですか？
これを
ファーストクラスの
これを直接にしとけばダメかな。
なんでだろう。
あれですよね、ファーストクラスのパスワードですよね。それ書いてないんだけどな。
じゃあファーストクラスに入れるかどうか試してみたい。
わかんねえや。
iOS の設定から多分しないといけない。
そうなんだ。ということで、ファーストクラスが使えますというのと、点と、そんな感じです。iPad ユーザーはそんなにいないので、まだしません。あ、僕ポチりました。ポチったの？iPad マジで？
数学的にはなんだ。
そもそもファーストクラス。
漢字ファイル名やったらダメかな。
こういうアプリがあって、Here is the application for reading the PDF file. And here is the function for you can select the size of the line and color like that. Then
ファイルストレージ。
so I always using this application to taking some memos for senior.
ペンはいくらで売ってるんですか
1980円。
そう
置けばいい。いい。
iPad のです。
すげえ。
これ何が素晴らしい What is the important thing is that you can export this one to
これで完了したんですか？
手軽です。
おお。でもそれ有料会員じゃないと。
いや、そういうわけじゃない。これは450円するけどね、アプリは。So that what I always doing is that first of all access to the first class like this. Okay, the first class application. Then maybe check the some post. This one is the seminars post. you can find some materials like this. You can read in the first class, but you can export this one to other application like notebook, 無印. Then the PDF file comes to the other application and you can open it. And you can write some memos.これ、今日中に私のブログにエントリーをアップしておくので
そちらから
そちらからどうぞこれプリンストンの確か1980年
ああ、お金が入ってくるんですね。
いやいや別に俺んとこからやれとは言わない
アフィ
アフィ iPad はこんな風に使うといいということです。そうするとファーストクラスに全てデータを置いとけば、大丈夫。あともう一個ごめん。Maybe some of you follow the SOAS project Twitter. So you know that the SOAS workshop named the SOAS Summer School to you. I changed the name SOAS workshop. And will be on 17th, 18th, 19th of September. All of you have to attend that one as a teaching assistant, research assistant, or staff. Okay, so